Next, we come upon our uniqueness results. So the first uniqueness result is that the multiplicative identity is unique. What does that mean? Well, suppose you have an element f in your group. Suppose that f times g is equal to g for all elements in your group. Then f is equal to the identity. The point is that the identity element is the only element in the group with this property. That's what makes it unique. This is one of those, if it looks like a duck and it quacks like a duck, then it is a duck theorems. So if you have an element that has these two properties for every element in the group, then it must be the identity element. So your group can't have two identities. It must have exactly one. To make calculations easier, I'm going to try to use slightly red font for this f. So f is this other identity we've happened to find that has the same property as the identity element we already proved existed using in whatever proof you use when you first proved that G was a group. Because remember, in the definition of a group, you know that at least one identity exists. So the point here is that that identity is unique. And so the proof is that we're going to compute f times e two different ways. One way we're going to see that this is equal to f, and the other way we're going to see that it's equal to e. And then therefore f is equal to e. So the first way is using this assumption. Since anything times f is anything, f times e is e. On the other hand, since e is a multiplicative identity, and we showed in the previous video that in a group, when you multiply on the right by the multiplicative identity, you get the same thing back, f times e is f. So we have f times e is e, f times e is f, therefore f and e are the same thing. So the identity is unique. Another important fact is that inverses are unique. So suppose you have a group, let h and g be two different elements. If g times h is equal to the identity, then h is equal to g inverse. So by the axioms of a group, there exists at least one element g inverse with this property. And the statement is that if you found another element with the same property, then they're actually the same. It's actually equal to G inverse. So not only do inverses exist, but every element has exactly one inverse. You can't find an element with two inverses. And here I'm going to use this assumption. We have GH equals E, but at the same time we just proved that multiplying on the right by G by an inverse gives you the identity as well. So G times G inverse is equal to E. And so we have GH is equal to G times G inverse. Oh, but we just proved the cancellation property too, so we can cancel out the G's and we have H equals G inverse. And that's exactly what we're going to do. And that's all she wrote. And so this is a different proof than the one done in the book. The one in the book does first principles, but here it's nice to use the cancellation property. And so you'll sometimes see this in courses where I don't always follow the textbook exactly, because sometimes I think it is better to reprove results using other results from the textbook. This also demonstrates another idea in mathematics, that sometimes we like to prove things using other things we have already proven, rather than just from first principles every time. And we immediately illustrate that concept of using facts to prove new facts by proving two formulas about inverses that follow from uniqueness of inverses. The first one is this fact, that if you take the inverse of an inverse of a group element, you get the group element back. Although my proof is by cancellation, but the proof in the textbook actually uses uniqueness of inverses as well. And so how do I do it? I just point out if you multiply on the left by G inverse, you get the identity. On the other hand, as we already pointed out in the previous video, multiplying an element on the right by its inverse also gives you the identity. So if you do cancellation, ignoring this little bit in the middle, you now have G is equal to its double inverse. But there's also proof in the textbook that uses uniqueness of inverses. And the next result I state is proven using uniqueness of inverses. So the next result is that the inverse of a product is the product of the inverses in reverse order. In other words, the inverse of AB is B inverse A inverse. Well, how would you go about proving such a result? Well, what does it mean to be the inverse? It means that if I multiply by AB, I better get the identity. So if this were true, what do I need to show? I need to show that when I do this product, I need to show this fact, and then I just apply uniqueness of inverses. And that would give me the result. In other words, if I show that this actually is the inverse, satisfies the same property as the inverse element, then it is the inverse element. So now we attempt to do that calculation. First thing we do is we apply associativity by treating AB as one element and then moving these parentheses over. Then we apply associativity again by treating A times B as two elements and moving the other pair of parentheses over so that we can get A times A inverse together inside a pair of parentheses so that we can cancel them and replace them with the identity. But the identity times anything is the other element, and so we have B by itself, and B inverse times B is also the identity. And so we found an element that canceled out AB and replaced it with E, and the inverse is the only one with that property. And so by uniqueness of inverses, the inverse of AB is B inverse A inverse. As one remaining fact, basic fact about groups, is if you're working in a group and A and B are elements of the group, then the equation AX equals B has a unique solution. So here X is an unknown. So the point is there's a unique element X for which this equation holds. Why is that true? Well, you can actually solve for X. So of course, normally they just give you the proof, but how do you actually find X? Well, let's get rid of the A by dividing by A. Oh wait, you can't divide, but you can multiply on the left by A inverse. And if you do that, what happens to the left-hand side? You get X. So X equals A inverse B. And so by trying to solve for X, we see this is the only this is the solution. And so if you plug this in, you will actually see that you get B out of it. And so what we see here is if this equation has a solution, then this is the format it is in. And you can check that this is a solution. Therefore, it is the unique solution. Now in this next part, we will talk about higher powers. So you can talk about exponentiation for group elements, but the exponents must be integers. So how do you define g to the n plus 1? Well, you define it as g to the n times g to the 1. So under this interpretation, g squared is just g times g. G cubed is just g squared times g. That's just g times g times g. And you see the point is that g to the nth power is just multiplying g by itself n times. However, you know that's slightly imprecise way of stating it, so the correct recursive way to define it is the way I just defined it, that g to the n plus first power is g to the nth power times g, with the special case that the 0th power is the identity element. And you can check that this actually gives the same definition, only for the purposes of proofs, this actually ends up being a lot more easier to work with than this other idea. So the other idea would be saying ... which is kind of a weird way to say things and harder to work with. So I prefer this approach for proofs. But in all practical purposes, it's actually the same idea. This is just the rigorous definition. You can also talk about negative powers, because g to the negative n is just going to be defined to be the nth power of the inverse. And so suppose we have this. There's reasons why we're going to want higher powers of a group element later in the course, actually very soon. But some properties of exponents for an arbitrary group is that g to the n plus m is equal to g to the n times g to the m. So this properties of exponents, these two properties of exponents both still hold in an arbitrary group as long as the base is fixed. And then the last property requires you to be working with an abelian group. It says that the nth power of a product is the product of the nth powers. You can see pretty quickly that this would make no sense for a non-abelian group, because for a non-abelian group, these two expressions with n equals 2 have this problem that the middle two terms are different. So you'd actually need h and g to commute with each other. So if h and g commute with each other, then this is true for all n. If h and g do not commute with each other, then this is false as soon as you hit n equals 2. I'm being slightly imprecise here. N and m should be arbitrary integers. And so we're going to prove these three facts. How are we going to prove it? Induction on m. Note, this isn't going to be a fully rigorous proof. I'm going to be trying to prove all three results simultaneously at once by induction on m. So of course, induction always has a base case. The base case is m equals 1. If you go through the three statements and you plug in m equals 1, note here that I'm using m in place of n for the statement in C, so it should be gh to the m equals g to the m, h to the m, in order for this statement to make sense, but that's a slight adjustment. And I'm completely ignoring negative numbers right now, so we have to go back later and figure out how to handle that. Or leave it as an exercise, which is kind of fun to do. So right now, it's worth pointing out this proof is only assuming that m is a non-negative integer. But either way, if you plug in m equals 1 into those three equations, this is what you get, and you see all three of them are true. So the base cases are true. So now we concern ourselves with m greater than 1. So let's look at statement A. We're looking at m plus 1, g to the n times g to the m plus 1. By my definition of exponentiation, that's g to the m times g. And what do I want to show? I want to show that this is equal to g to the n plus m plus 1. It's worth noting here, what am I trying to do? I'm assuming some statement for m, and I'm going to try to prove the statement worth m plus 1. That's what I'm doing here, because that's what you do in the inductive step. Well, now I use associativity to move the parentheses over. Why? Because I'm doing a proof by induction, and I can apply the induction hypothesis to g to the n times g to the m. And that's exactly what I do. By the induction hypothesis, that's g to the n plus m. Oh, but my definition of exponentiation is that g to the n plus m plus 1 is g to the n plus m times g. It's a very handy definition. So that's it for A. Notice I started with the factored form on the right-hand side. That will probably be true for B as well. So let's go to B. I'm looking at g to the n plus first power. Well, what's the definition of x to the m plus first power? It's x to the m times x. If I substitute g to the n for x here, I get g to the n to the m times g to the n. So I'm just applying my definition of exponentiation, where the base is g to the n and the exponent is m plus 1. Now I use my induction hypothesis. G to the n to the m is g to the n times m. And now I use part A, which I've now already finished the proof of by induction, so I can use it here. Powers add. So n times m plus n. And now I can factor out the common factor of n. So by doing arithmetic, I've got exactly what I wanted. G to the n to the m plus first power is g to the n times m plus 1. So if I raise a power to a power, the powers multiply by induction. Finally, for part C, let's compute the m plus first power of g times h. Well, by definition of exponentiation with base g times h, that's the mth power of g times h times g times h. By the induction hypothesis, gh to the mth power is g to the mth power times h to the mth power. Since my group is abelian, I'm going to be able to h to the m times g is equal to g times h to the m. So this is where I use commutativity, and then my definition of exponentiation says I can rewrite these as powers of g times powers of h. And so that is what I do. And so now I've finished the proof in the case where m is a non-negative integer power. All three of these properties hold by induction on m. Now, of course, this begs the question of what happens when m is a negative power. Well, I can leave you to figure out how to handle that. That takes a little bit more work, but it can also be done. But obviously, it can't be done by induction itself, so it's going to take a separate argument.